want to ask you a question, and I want you to really sit with it before you answer. Not the quick answer, the one that comes automatically, the one you learned somewhere and filed away and never really examined. I want the answer you arrive at when you actually think about it. How big is the universe? Go ahead, think about it. What comes to mind, probably something like infinite, endless, stretching forever in every direction, with no boundary and no edge and no wall, where space stops and something else begins. That is the picture most people carry. The universe as an infinite three-dimensional expanse going on in every direction without limit. That probably, and if you are being honest with yourself, you probably never really questioned that picture, because infinity is a comfortable answer. It wraps the problem up neatly. If the universe is infinite, then you never have to ask what is beyond it. There is no beyond. Problem solved. Move on. But here is the thing. We do not know that the universe is infinite. We have never known that. It is an assumption, a default, a picture we defaulted to in the absence of evidence pointing elsewhere. And the evidence, the actual data we have been collecting about the structure and geometry and large-scale behavior of the cosmos has been quietly and persistently and with increasing insistence been pointing somewhere else, somewhere stranger, somewhere that requires you to throw out the comfortable picture entirely and replace it with something that your intuitions are not going to handle gracefully. And the universe may have an edge. Now, before you dismiss that as science fiction, I need to be precise about what I mean, because the word edge carries a lot of baggage. When you hear edge, you probably picture something like the edge of a table or the edge of a cliff. You picture space going on and then stopping. And at the stopping point, some kind of wall or boundary or drop off into nothing. And then you immediately ask the obvious question: what is on the other side of the wall? What is beyond the edge? And the question feels like it refutes itself, because surely if you can ask what is beyond, then the edge is not really an edge. There must be something on the other side. And that something is part of the universe too. So the universe is bigger than you thought. No edge after all. But that reasoning only works if you assume that space behaves the way a table behaves, that it is embedded in some larger space, that it sits inside of, and that larger assumption is exactly what modern cosmology is questioning. The edge of the universe, if it exists, is not an edge in the way a table has an edge. It is something far stranger, something written into the geometry of space itself. A boundary that is not a wall you bump into, but a feature of the mathematical structure of reality at the deepest level, cumbrous. And when physicists say the universe might have an edge, they are pointing to several different but related possibilities, each one more mind-bending than the last. And each one supported by real data, real observations, real mathematical frameworks that are being actively developed and debated right now in the most prestigious physics departments in the world. That is what we are going to explore today. And I promise you that by the time we are done, the word infinity will never mean the same thing to you again. Let us start with what we actually know. Because what we actually know is itself extraordinary. We know that the universe began approximately 13.8 billion years ago in an event we call the Big Bang. Not an explosion into pre-existing space. Not a firecracker going off in an empty room, but a rapid expansion of space itself from an extraordinarily hot, dense state. Space did not expand into anything. Space itself expanded. The distances between points in space increased. And as space expanded, it cooled. Prostate. And as it cooled, the energy that filled it condensed into particles. And those particles formed hydrogen and helium clouds. And gravity pulled that hydrogen and helium into clouds. And the clouds collapsed into stars. And the stars forged heavier elements in their cores and scattered them across space when they died. And from those heavier elements came planets, chemists. And on at least one of those planets came chemistry. And from that chemistry came life, brains. And from that life eventually came creatures with brains, complex enough to look up and ask how it all began. That is the story. And we know it with extraordinary confidence. Not because someone told it to us, but because we can see the evidence. We can detect the afterglow of the Big Bang itself. The cosmic microwave background radiation. A faint glow of microwave radiation filling the sky in every direction. The cooled remnant of the light that filled the universe when it was about 3,800,000 years old. Before that point, the universe was so hot and dense that it was opaque. Light could not travel freely. Electrons and protons had not yet combined into neutral hydrogen atoms. The universe was a plasma, an opaque fog of charged particles. And then at 3,800,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine. The fog lifted. Light was suddenly free to travel. And that light has been traveling ever since for 13.8 billion years through an expanding universe, getting stretched to longer and longer wavelengths by the expansion until today it reaches our detectors as microwave radiation. The oldest light in the universe is a photograph of the cosmos when it was an infant. And that photograph contains information, extraordinary information about the geometry of the universe, about its composition, about its age and its fate. And it is in that information that the first hints of an edge appear. Here is what I mean. The cosmic microwave background is not perfectly uniform. It has tiny temperature fluctuations, hot spots and cold spots, variations of about 1 part in 100,000, tiny, but real. And the pattern of those fluctuations, the statistical distribution of hot and cold spots of different sizes, is a fingerprint of the geometry of the universe. Here is the key insight. Sound waves were propagating through the hot plasma of the early universe before the fog lifted pressure waves. Acoustic oscillations. The same physics that governs sound waves in air governs these fluctuations in the plasma. And those waves have a characteristic scale, a characteristic size of the patterns they produce, determined by how far sound could travel in the 380000 years before the fog lifted. Physicists call this the sound horizon in day. Now here is where geometry comes in. If the universe is flat, if space has no curvature on large scales, Beck, then the angular size of those characteristic patterns, as we see them today in the cosmic microwave background, should be about 1 degree. 1 degree across the sky. Positive, if the universe is positively curved, like the surface of a sphere, then those patterns should appear larger than 1 degree, magnified by the curvature. If the universe is negatively curved, like the surface of a saddle, then they should appear smaller, demagnified. We measure those patterns. We have been measuring them with exquisite precision for decades. First with ground-based telescopes, then with the COBE satellite, then with WMAP, and most recently with the Planck satellite. And the answer we get is flat. The universe is geometrically flat to within about 0.5%. Space on the largest scales we can probe has no detectable curvature. The angles of a cosmic triangle add up to 180 degrees. Euclid would be satisfied. But here is what flat does not mean. Flat does not mean infinite. This is the confusion I want to dispel right now, because it is at the heart of why this story is so surprising. Think about a flat piece of paper. It is flat. It has no curvature, but it has edges. It is finite. Now roll that piece of paper into a cylinder. The cylinder is still flat in the geometric sense. If you draw a triangle on the surface of a cylinder, the angles still add up to 180 degrees. Flatness is preserved. But the cylinder is finite. And if you were a two-dimensional creature living on the surface of that cylinder, you would eventually come back to where you started if you traveled far enough in one direction. The space wraps around on itself. It is finite, but it has no edge in the sense of a boundary you bump into. You just return to your starting point. The universe could be like that. Flat in the geometric sense, finite in volume, but with no boundary. A topology that wraps around on itself in 3 dimensions, a 3-dimensional analog of the cylinder surface, or something more exotic, a 3-dimensional torus, or a space with an even more complex topology. The geometry tells you the local shape of space. The curvature, the topology tells you the global structure, how space is connected to itself. And geometry and topology are independent. You can have flat space with almost any topology. So when we measure the universe to be flat, we have not measured it to be infinite. We have measured the local curvature, the global structure, the topology remains to be determined. And this is where the question of an edge gets really interesting. Because there is another kind of boundary that the universe might have. One that is not about topology at all. One that is about something more fundamental, about the nature of space itself, at the very edge of the observable universe and beyond. Let me tell you about the observable universe, because this is a concept that is absolutely central to everything that follows, and that most people do not fully appreciate the implications of. The observable universe is the region of space from which light has had time to reach us since the Big Bang 13.8 billion years of travel time. You might think that means the observable universe is 13.8 billion light years in radius, but it is not. Because while the light was traveling, the universe was expanding. Space itself was stretching. The source of the most distant light we can see was only about 42 million light years away when it emitted that light 13.8 billion years ago. But in the time it took that light to reach us, the universe expanded so much that the source is now about 46 billion light years away. The observable universe is a sphere about 93 billion light years in diameter, centered on us. And beyond that sphere, there's almost certainly more universe, more space, more matter, more galaxies. We just cannot see it, because light from those regions has not had time to reach us. Those regions are beyond our cosmic horizon, not beyond the edge of space, beyond the edge of what is visible to us from our particular location at this particular time. Now, here is the question that haunts modern cosmology. What is out there beyond the observable universe? Is it more of the same? More galaxies stretching on forever in a universe that really is infinite? Or does something change? Does space eventually behave differently at enormous distances? Does it curve back on itself? Does it reach a boundary? Does it end? For decades, the default assumption was more of the same. The cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, the same in every direction, the same everywhere. No special locations, no edges, no boundaries, more of the same stretching on to infinity. But the data has been accumulating, and some of it is not comfortable. Some of it is distinctly not what you would expect from a perfectly uniform, infinite universe. Let me tell you about one of the most discussed and controversial anomalies in modern cosmology, the large-scale anomalies in the cosmic microwave background. That when the Planck satellite produced the most precise map ever made of the cosmic microwave background, something unexpected appeared. The fluctuations on very large angular scales. The largest patterns across the sky were weaker than predicted, significantly weaker. The large-scale power was suppressed, not dramatically, not in a way that screams obviously wrong, but persistently, reproducibly, consistently showing up across multiple experiments with multiple independent analyses. In an infinite universe with no preferred scale, you would expect fluctuations at all scales. Large patterns and small patterns distributed in a specific way, predicted by the standard model of cosmology. But the largest patterns are quieter than they should be, as if space is not big enough to support those very large-scale oscillations, as if the universe has a size, a scale beyond which the fluctuations simply do not exist because there is no more universe to fluctuate. Think about what that means. Sound in a room. If you play a note in a small room, you can only sustain certain frequencies. The wavelengths that fit in the room, wavelengths larger than the room, simply cannot be sustained. They do not fit. Parasis. And if you analyze the sound in that room, you will find a deficit of very long wavelength components. The room has imposed a minimum frequency a maximum wavelength, a scale set by the size of the space. If the universe has a size, a finite extent, then there will be a maximum wavelength for primordial fluctuations, a largest possible pattern wavelength. And we should see a deficit of fluctuations on scales larger than that maximum wavelength, which is exactly what we see. The suppression of large scale power in the cosmic microwave background is consistent with a universe that has a finite size comparable to or not vastly larger than the observable universe. Now, I want to be careful. This anomaly has been known for years, and it is genuinely debated. Some physicists think it is a statistical fluke, a 1 in 20 chance fluctuation that looks significant but is not. Others think it is a measurement artifact, a contamination from our own galaxy or from some other systematic effect. But it has not gone away. Every new analysis finds it. Every new data set confirms it. And the statistical significance is not trivial. It sits at a level that keeps serious cosmologists up at night. And it is not the only anomaly. There's the hemispherical power asymmetry. The fact that one hemisphere of the cosmic microwave background sky has slightly more power in its fluctuations than the opposite hemisphere. An asymmetry that should not exist if the universe is the same in every direction. There's the cold spot, a region in the southern sky that is anomalously cold by about 70 microkelvin compared to what the standard model predicts. Significantly colder, with a size of about 5 degrees across the sky. Something made that region cold. And the explanations that have been proposed range from a statistical fluke to a supervoid in the large-scale structure to something far more exotic that involves the structure of space itself. These anomalies individually might be dismissed. Statistically unlikely events happen. 1 in 20 chances come up, 1 in 20 times. But the accumulation of anomalies, the fact that they cluster on large angular scales, the fact that they all seem to be telling us something about the very largest structures in the universe, that accumulation is harder to dismiss. And it is pushing cosmologists to ask whether the standard picture of an infinite homogeneous universe is actually correct. And here is where the theoretical ideas become as interesting as the observational ones. Because the question of whether the universe has an edge is not just an observational question, it is a theoretical question. And the theory that is most naturally equipped to answer it is the same theory that tells us what happened at the very beginning of the universe. It's inflation. If you have heard of inflation, you know it as the theory that in the first tiny fraction of a second after the Big Bang, the universe underwent an extraordinarily rapid exponential expansion, expanding by a factor of at least 10 to the power of 26 inches, an interval of time so short, it makes a billionth of a second look like an eternity. This rapid expansion is what explains why the universe is so flat, why it is so uniform, why the cosmic microwave background looks almost identical in every direction, even though opposite sides of the sky could not have been in causal contact without inflation. Inflation is the mechanism that set up the initial conditions that the standard cosmological model takes as given. But inflation has a feature that is both its greatest triumph and its greatest challenge. Inflation, once started, is extraordinarily difficult to stop everywhere simultaneously. In most models of inflation, the quantum fluctuations in the inflatant field, the field driving the inflation, cause some regions to stop inflating while others keep going. The regions that stop inflating become bubble universes, regions of normal physics like ours. But the space between those bubbles keeps inflating exponentially forever, producing more bubbles, more pocket universes, each one potentially with different physical constants, different laws, different histories. This is eternal inflation, and it implies that our observable universe, our bubble, is embedded in an eternally inflating space that is vastly larger, possibly infinite. But our bubble itself, the region where inflation ended and normal physics began, that bubble has a finite size. It has a boundary, not a wall you can travel to, because the boundary is not in space. It is in the structure of what happened during inflation. It is the edge where our particular episode of inflation ended and the surrounding eternal inflation continues. Now, here is where it gets philosophically vertiginous. If inflation ended in our bubble to create our universe with our physical constants, our laws of physics, our particle masses and coupling constants, then other bubbles formed in other regions of the eternally inflating space might have different physical constants, different laws, different values of everything we regard as fundamental. The multiverse of eternal inflation is not just a collection of universes that are far away. It is a collection of universes that are genuinely different, different physics, different chemistry, possibly no atoms, possibly no stars, possibly structures we cannot even imagine, because our imaginations are built from the physics of our bubble and the boundary between our bubble and the surrounding eternal inflation. That is one candidate for the edge of the universe. Not an edge you can reach, not an edge you can point toward, but an edge that is written into the history of how our particular region of space-time came to exist. But there is another candidate for the edge, one that comes not from inflation, but from quantum gravity. And this one is even stranger. Let me tell you about the no boundary proposal, because this is one of the most beautiful and disturbing ideas in all of theoretical physics, and it directly addresses the question of what the edge of the universe is, or whether the question even makes sense. The no boundary proposal was put forward by Stephen Hawking and James Hartle in 1983. And it attempts to answer the question that cosmology ultimately cannot avoid: what came before the Big Bang? What were the initial conditions of the universe? Where did they come from? The standard Big Bang model tells us that the universe began in an extraordinarily hot, dense state and has been expanding and cooling ever since. Bliner. But it does not tell us why it began in that state. What determined the initial conditions? What chose the specific configuration of matter and energy and geometry from which our universe grew. These are questions that general relativity cannot answer, because general relativity breaks down at the Big Bang, just as it breaks down at the singularity inside a black hole. The equations produce infinities. The theory fails. Something deeper is needed. Hartle and Hawking proposed that the something deeper is a quantum theory of the universe as a whole, a wave function of the universe. A quantum mechanical description, not of particles in space, but of space itself, of the geometry of the universe, as a quantum object subject to the superposition and uncertainty and probabilistic evolution of quantum mechanics. And in their proposal, the wave function of the universe has a specific and remarkable feature. In ordinary quantum mechanics, a particle has a wave function that evolves in time. You specify the initial state, the wave function, at some starting time, and the equations tell you how it evolves forward. But where did the initial state come from? You always need a boundary condition, something to start with. Hartle and Hawking proposed that the universe has no such boundary, no initial state that was somehow imposed from outside. Instead, they proposed that the universe is a quantum object whose wave function is defined by a sum over all possible geometries of space-time that are compact, that have no boundary, no edge, no initial moment where you have to impose a boundary condition from outside. The key insight is that in quantum gravity, time itself is not fundamental. Time emerges from the geometry of space-time. And in the very early universe, when quantum gravitational effects are dominant, time as we understand it did not exist. The distinction between time and space was not sharp. In the Hartle-Hawking proposal, the early universe is described by a geometry that is purely spatial, that has no time direction, a geometry that is finite and closed and smooth with no beginning and no edge, like the surface of a sphere, which is finite and has no boundary and no special point that you could call the beginning. Baya. And then as the universe evolved and expanded and cooled, time emerged from this timeless quantum geometry. The distinction between space and time sharpened. The classical universe we inhabit grew from a quantum seed that had no beginning and no edge in time, because time itself was not yet a meaningful concept. Now, I want to be honest with you. The no boundary proposal is beautiful. It is mathematically sophisticated controversy, and it addresses a question that every other approach leaves unanswered. But it is deeply controversial. The mathematical details of how to define the sum over geometries properly are not settled. Different approaches to calculating the wave function give different answers. Some recent work has suggested that the no boundary wave function actually predicts that the most likely universes to emerge are not large and smooth like ours, but small and highly curved, which would be a serious problem for the proposal as a description of our universe. The debate continues. The mathematics is hard. The physics is harder. But the idea itself, the idea that the universe might have no boundary in a precise mathematical sense, that the question of what is beyond the edge might be as confused as the question of what is north of the North Pole. That the geometry of space-time itself might be the answer to the question of its own origin. That idea is one of the most profound that human beings have ever had. Power. And it sets up the question that I want to leave you with before we go deeper in the second part of this story. If the universe has no boundary in the Hartle-Hawking sense, then asking what is beyond the edge of the universe is like asking what is north of the North Pole. The question assumes a framework that does not apply. It assumes that the universe is embedded in something larger, that there is an outside bilaterus. And the no boundary proposal says there is no outside. The universe is all there is. The geometry is closed. The wave function is defined without reference to anything external. The universe is self-contained in the deepest possible sense. But if eternal inflation is correct, then our bubble universe does have a boundary of sorts. The edge where our inflation ended and the surrounding eternal inflation continues. And beyond that edge are other bubbles, other universes. A vast, possibly infinite landscape of pocket universes, each one, a cosmos in its own right. These two pictures are not necessarily incompatible, but they point in very different directions about what the edge of the universe means. And new data, new observations, new theoretical developments are beginning to let us discriminate between them. The cosmic microwave background anomalies I described are one line of evidence. But there are others. The large-scale structure of the universe, the distribution of galaxies across billions of light years, the statistics of galaxy clustering, the behavior of dark energy, the subtle imprints that a finite universe topology would leave on our observations. All of these are being mined for clues about the true geometry and topology and extent of the cosmos. And there is one more possibility that I have not yet told you about. One more candidate for the edge of the universe that is perhaps the most radical of all. That comes not from inflation or quantum cosmology, but from the frontier where quantum gravity and thermodynamics and information theory collide. The possibility that space itself has phases, that what we call space. The smooth, continuous geometric structure that general relativity describes is not the fundamental thing, that it is an emergent phenomenon, like temperature, like pressure, like solidity, properties that emerge from something more fundamental at smaller scales. And that at the very edge of the universe, at the boundary of the observable cosmos, or at some scale we have not yet probed. Space might undergo a phase transition, might change its character, might transition from the familiar geometric space we inhabit into something else entirely. Something for which we do not yet have the right words or the right mathematics. Because the mathematics that would describe it is the mathematics of quantum gravity, and we do not yet fully have that mathematics. That possibility, the possibility that the edge of the universe is not a wall and not a wraparound and not the boundary of a bubble, but a phase transition in the fabric of reality itself. That is where we are going in part 2. And I promise you, it is worth the journey. Ready to continue with part 2? Has Daiko CC1201 PM. Claude Ha Respondido. Scientists just discovered the universe has an edge. Scientists just discovered the universe has an edge. Part 2, let me tell you about a phase transition. Not a cosmic one. Not yet. Let me start with something you have experienced. Something so ordinary that you have probably never stopped to think about how extraordinary it actually is. Water. You have seen water as a liquid. You have seen it as ice. You have seen it as steam. 3 states of the same substance, 3 phases. And the transition between them is not gradual. It is not a slow, continuous change where the water gets a little more ice. Like with every degree you cool it, the transition is sharp, discontinuous. At exactly 0 degrees Celsius, at standard pressure, liquid water becomes ice. At exactly 100 degrees, it becomes steam. One moment you have a liquid, the next you have a solid. The molecular structure reorganizes. The properties change dramatically. The same collection of H2O molecules that were flowing freely past each other are now locked into a rigid crystalline lattice. The same substance, completely different behavior, completely different properties, separated by a sharp boundary in temperature called a phase transition. Water. Now here is the question that I want you to hold in your mind. The question that connects a glass of ice water to the edge of the universe. Could space itself undergo a phase transition? Could the smooth, continuous, geometric fabric that we call space-time, the stage on which all of physics plays out, the thing that general relativity describes with such extraordinary precision, could that fabric be a phase of something more fundamental, a specific organized state that the underlying quantum degrees of freedom settle into under certain conditions? And could there be other phases, other ways that those underlying quantum degrees of freedom could organize themselves that would produce something that looks nothing like the space we know? This is not a casual speculation. This is one of the central ideas emerging from the intersection of quantum gravity and condensed matter physics. 2 fields that seem to have nothing to do with each other and that have been producing some of the most surprising cross-pollinations in all of contemporary science. Here is the background you need. In condensed matter physics, the study of how large collections of particles organize themselves into materials with different properties. Physicists have developed extraordinarily powerful tools for understanding emergence. How simple underlying constituents, following simple rules, give rise to complex collective behaviors that look nothing like those rules. How electrons in a metal organize themselves into a superconducting state where electrical resistance vanishes entirely. How liquid helium below a certain temperature becomes a superfluid that flows without any viscosity whatsoever. How magnetic materials develop long-range order. How simple models of interacting spins on a lattice give rise to rich phase diagrams with multiple distinct phases separated by sharp transitions. Kundalini. And the key insight that has been migrating from condensed matter physics into quantum gravity is this. The properties we associate with space, its smoothness, its geometry, its dimensionality, its causal structure, these properties might be collective properties, emergent properties, properties that arise from the organized behavior of some underlying quantum system. In the same way that rigidity and conductivity and magnetism arise from the organized behavior of electrons in a solid. If that is true, then space is not fundamental. Space is a phase, our space. The three-dimensional, smoothly curved Lorentzian spacetime of general relativity is one particular organized state of some underlying quantum system. And like any phase, it has boundaries, conditions under which it exists, and conditions under which it does not. Now, let me make this concrete, because I know this sounds abstract, and I want to give you the physical intuition. In loop quantum gravity, one of the leading approaches to a quantum theory of gravity space is not continuous. It is not smooth at the smallest scale, the Planck scale, but 10 to the minus 35 meters, vanishingly smaller than anything we can currently probe. Space is discrete, granular, built from fundamental quantum units of geometry, quanta of area and volume. These quanta are connected to each other through a network of relationships described by mathematical objects called spin networks. Phase. And the smooth, continuous space of general relativity emerges from this discrete network, the way a smooth surface of water emerges from the collective behavior of an enormous number of individual water molecules. The smoothness is not fundamental. It is statistical. It is the result of averaging over an enormous number of discrete quantum geometric elements. And here is what that means for the edge of the universe. If space is a collective emergent phenomenon built from discrete quantum geometric units, then it is possible, theoretically possible, mathematically coherent, to have regions where the collective organization breaks down, where the quantum geometric units fail to organize into the smooth geometric structure we call space, where you cross from a region of organized geometric order into a region of quantum geometric disorder, where space as we know it simply stops existing and is replaced by something that has no geometry in the classical sense, no distances, no directions, no causal structure, just the raw underlying quantum degrees of freedom in a disordered phase. That would be an edge, not a wall, not a boundary in space, a boundary of space itself. The place where space ends, not by stopping like a tabletop, but by dissolving, by losing its organized collective structure and becoming something else. Something prior to geometry, something from which geometry emerges under the right conditions, but which is itself not geometric. Think about what it would mean to reach that edge. You cannot reach it by traveling in a direction because direction is a geometric concept. And at the edge geometry fails aske. You cannot ask what is on the other side, because the other side is not a spatial relationship. It is a phase of the underlying quantum system for which our spatial language has no purchase. The edge of the universe in this picture is not a place. It is a condition, a boundary between a phase where space exists and a phase where it does not. Comp. And here is what makes this more than just philosophical speculation. There are observational signatures, fingerprints that this kind of structure would leave on the universe we can observe, fingerprints that we are beginning to have the tools to look for. If space is emergent from a discrete quantum structure, then at sufficiently small scales or equivalently at sufficiently high energies, the smooth geometric structure should show signs of breaking down. The propagation of light through this granular space-time should be subtly different from propagation through perfectly smooth space. High energy photons should travel at very slightly different speeds than low energy photons, an effect called Lorentz invariance violation. We have been looking for this effect for years, using gamma ray bursts, extraordinarily energetic explosions at cosmological distances that produce photons across a huge range of energies simultaneously. If the granular structure of space-time causes high energy photons to travel at slightly different speeds, then after traveling billions of light years, the high energy photons should arrive at slightly different times than the low energy ones. We have looked, so far we have not detected this effect, which puts very tight constraints on the scale at which the granular structure appears. But the search continues with better instruments and more sensitive measurements. And there is another signature. If the universe has a finite size comparable to the observable universe, then the topology of space should leave imprints on the cosmic microwave background. Not just in the suppression of large-scale power that I described in part 1, but in specific patterns of correlation, in matched circles, in the cosmic microwave background. If the universe wraps around on itself, then some circles on the sky should show identical patterns of temperature fluctuations, because those circles are actually the same physical region of space seen from different directions, like seeing the same wall of a room from two different positions. We have looked for matched circles in the cosmic microwave background. The searches have been challenging, and the results have been inconclusive, but not definitively negative. The universe could have a topology that wraps around on a scale somewhat larger than the observable universe, and we would not yet have detected it. And there is the question of dark energy, the mysterious component that makes up about 68% of the total energy content of the universe, and that is causing the expansion of the universe to accelerate. We discovered the acceleration of the expansion in 1998. Two teams of astronomers using type Ia supernovae as standard candles to measure distances across the universe found that the most distant supernovae were fainter than expected, farther away than they should be if the expansion were decelerating under the influence of gravity. The expansion was not decelerating. It was accelerating. Something was pushing space apart, faster and faster. We called it dark energy. We assigned it a symbol in the equations, the cosmological constant, lambda. And we moved on, having named the mystery without solving it, ander. But dark energy might be the most important clue we have about the edge of the universe, because dark energy determines the ultimate fate of space, and its behavior at very large scales might tell us something about the structure of space at those scales. If dark energy is a true cosmological constant, a fixed property of empty space that does not change with time or location, then the universe will expand forever. Galaxies will recede from each other faster and faster. Eventually, each galaxy or gravitationally bound cluster of galaxies will be an island in an expanding desert. The cosmic microwave background will be redshifted beyond detectability. The observable universe will shrink as the expansion carries more and more regions beyond our horizon. In the far future, a civilization in our galaxy would look out and see only its own galaxy in an otherwise dark and empty cosmos. Every other galaxy having receded beyond the horizon. They would have no evidence from observation that the universe was ever filled with other galaxies. The information about the wider universe would be lost to them forever. But if dark energy is not a cosmological constant, if it is a dynamic field, an energy that evolves with time, then its future behavior is uncertain. It could weaken, the acceleration could slow, or it could strengthen. In some models, dark energy grows over time, becoming stronger and stronger until eventually it tears apart not just the large-scale structure of the universe, but galaxies, and then solar systems, and then planets, and then atoms, and then the fabric of space-time itself. In a scenario called the Big Rip, the expansion accelerates so dramatically that in a finite time, the scale factor of the universe reaches infinity. Space is torn apart, not at some edge, everywhere simultaneously. Every point in space receding from every other point at faster than light speed. The ultimate edge, not a boundary of space, but the end of space. The phase transition from space to nothing happening everywhere at once. The Big Rip is not the most likely scenario given current data. The data is most consistent with a cosmological constant that is not growing, it is not ruled out. And the measurement of how dark energy behaves over cosmic time, whether it is truly constant or whether it is evolving, is one of the central scientific goals of the next generation of large-scale surveys. The Euclid satellite launched in 2023, and the Vera Rubin Observatory now coming online, and the Nancy Grace Roman Space Telescope scheduled for launch in the coming years, will all measure the expansion history of the universe with unprecedented precision. They will tell us whether dark energy is constant or dynamic. And that answer will tell us something profound about the ultimate fate and possibly the ultimate structure of space. Con. Now I want to take you somewhere even deeper, somewhere that requires us to revisit the most fundamental assumptions we make about the nature of reality. Because the question of whether the universe has an edge ultimately forces us to confront a question that physics has been circling for decades without quite being able to land on it. What is space? Not what is in space. What is space itself? What is the thing that has an edge or does not have an edge? The thing that curved or is flat? The thing that is expanding or might be finite? What is the fundamental nature of the geometric fabric of reality? General relativity treats space, or more precisely space-time, as a physical thing, a dynamic entity that can curve and stretch and ripple, not a fixed background against which physics happens, but an active participant in the physics. The curvature of space-time is gravity. The ripples of space-time are gravitational waves. Space is real. It has physical properties. It can be measured. But quantum mechanics treats space very differently. In quantum field theory, the standard framework for describing particles and forces particles are excitations of quantum fields. The electron field, the photon field, the quark fields. These fields fill all of space, and space is the arena in which they exist, the background, the stage. Space in quantum field theory is not dynamic the way it is in general relativity. It is fixed. It is the container reconciling these two pictures, making space both the dynamic curved entity of general relativity and the fixed background of quantum field theory. It is the central challenge of quantum gravity, and the most promising approaches to solving it all point toward the same conclusion. Space is not fundamental. Space emerges. We have talked about this in the context of loop quantum gravity, but the most mathematically precise version of this idea comes from a completely different direction. From the holographic principle and its most concrete realization, the ADS CFT correspondence that I mentioned when we talked about black holes. Let me remind you of what ADS CFT says. It says that a theory of quantum gravity in a certain kind of spacetime called anti-de Sitter space is exactly equivalent to a quantum field theory with no gravity living on the boundary of that spacetime. The two theories are dual. They describe the same physics in different languages. And crucially, the quantum field theory on the boundary has one fewer dimension than the gravitational theory in the bulk. The three-dimensional bulk gravitational theory is equivalent to a two-dimensional boundary theory. The third dimension, the depth of the bulk, emerges from the quantum field theory on the boundary. It is not fundamental. It is encoded. It is holographic, pine. And what determines how the bulk dimension emerges? What creates the depth, the geometry, the space inside the bulk? It is the entanglement structure of the boundary quantum field theory, the way different regions of the boundary are quantum mechanically correlated with each other. More entanglement between boundary regions corresponds to more connected geometry in the bulk. Less entanglement corresponds to less connected geometry. Regions of the boundary that are not entangled with each other correspond to bulk regions that are geometrically disconnected. Where space does not exist between them in the usual sense. This is the ER equals EPR idea again, but now in the context of the whole universe rather than just black holes. The geometry of space, the distances between points, the connections between regions, all of it is encoded in and generated by quantum entanglement. Space is woven from entanglement. The fabric of the cosmos is a quilt stitched together by quantum correlations. And if that is true, then the edge of the universe, the boundary of space, is the place where the entanglement runs out, where the quantum correlations that weave space together thin out and fail, where the quilt ends, not because someone cut it off, but because there are no more threads to weave. And the edge of the universe is the edge of entanglement. The boundary of the quantum correlations that generate space. Condor. Now, think about what that means observationally. We cannot directly observe the entanglement structure of the universe. Conator. We cannot reach out and measure the quantum correlations between distant regions of space. But the entanglement structure determines the geometry, light, and the geometry determines how light travels, how matter clusters, how the cosmic microwave background looks. The large-scale anomalies we see in the cosmic microwave background, the suppression of large-scale power, the hemispherical asymmetry, the cold spot, these are all deviations from what a perfectly homogeneous, infinite, uniformly entangled universe would look like. They are the fingerprints of a universe whose entanglement structure is not uniform, not infinite, not the same in every direction. They're hints of the edge. X. Now, I want to address the question that has been building throughout this entire conversation. The question that every person who has followed this far is asking, even if they have not quite put it into words, if the universe has an edge, what is beyond it on this clue? And I want to give you the most honest answer I can, which means I have to tell you something that is philosophically uncomfortable but scientifically important. The question might not be meaningful. I do not mean that as a dodge. I mean it as a precise physical statement. The question, what is beyond the edge of the universe, assumes that beyond is a spatial relationship. That the edge of the universe is embedded in some larger space, such that there is a region of that larger space on the other side of the edge. But if the edge of the universe is the edge of space itself, the boundary of the emergent geometric structure, the place where entanglement runs out and space dissolves into its quantum constituents, then beyond is not a spatial relationship that applies. There is no spatial beyond. There's no other side in the geometric sense. What there might be is a different phase of the underlying quantum reality, a phase in which our geometric intuitions simply do not apply. A phase that cannot be described in terms of distances and directions and locations, because those concepts require space. And space is what this phase does not have. Asking what is beyond the edge of the universe is like asking what is north of the North Pole. The question assumes a coordinate system that breaks down at the very point you are asking about. But here is what I find genuinely magnificent about that answer. It is not a defeat, it is a discovery. The discovery that the universe does not owe us a geometry beyond its own boundary. That the framework we use to describe the universe, space and time and distance and direction, is a framework that applies within the universe and not outside it. not because there is something hiding outside that we cannot reach, but because outside in the geometric sense does not exist. The universe is not inside something larger the way a room is inside a building. The universe is not floating in some pre-existing space. The universe is the space. It generated the geometry. It is not embedded in anything more fundamental in a spatial sense. And yet, there is something more fundamental. The quantum degrees of freedom from which space emerges, the entanglement structure that weaves the geometric fabric, the underlying quantum reality that has space as one of its phases, that something exists. It is not nothing. It is not empty. It is the most real thing there is, more fundamental than space itself. There isn't any. And we do not yet have the right language or the right mathematics to describe it fully, because our language was built for a world of space and time. Prior, and this, something is prior to space and time. This is where physics stands right now, at the edge of its own conceptual framework, looking out at a question that requires new concepts, new mathematics, new ways of thinking about what existence means when space itself is not guaranteed. And I want to tell you something about that position, about standing at the edge of what is known and looking into the unknown. I have been a scientist for my entire adult life. I have watched science make discoveries that would have seemed impossible to previous generations. We have detected gravitational waves from colliding black holes 1 billion light years away. We have photographed the shadow of a black hole 55 million light years distant. We have mapped the cosmic microwave background with enough precision to determine the age and composition and geometry of the universe to within a fraction of a percent. We have done things that would have seemed like magic to scientists of a century ago. And every time science has approached a boundary, every time the equations have broken down and the theories have failed and the data has pointed somewhere unexpected, every time that has happened, it has meant that something new was waiting, something deeper, something more fundamental, something that, when it was discovered, made the previous understanding look like a rough sketch of a much more detailed picture. The singularity at the center of black holes is pointing toward quantum gravity. The anomalies in the cosmic microwave background are pointing toward something about the true size and structure of the universe. The dark energy accelerating the expansion is pointing towards something fundamental about the nature of space and vacuum energy. The holographic principle is pointing toward space as an emergent phenomenon woven from entanglement. All of these arrows are pointing in the same direction, toward a revolution in our understanding of space and time and the nature of the universe at the deepest level. A revolution that has not yet fully arrived, but that is coming. The physicists working on these problems right now, the young researchers in their 20s and 30s sitting in offices at Caltech and MIT and the Perimeter Institute and the Max Planck Institute, filling blackboards with equations that most people on Earth will never see, wrestling with the mathematics of quantum gravity and the topology of the universe and the entanglement structure of space-time. They are doing something that I think deserves more recognition than it gets. They are pushing the boundary of what our species understands about the nature of existence itself. They're extending the reach of the human mind into territory that no human mind has ever reached before. And they're doing it with the same tools that Galileo used. Observation, mathematics, logical reasoning, the willingness to follow the evidence wherever it leads, even when it leads somewhere that overturns everything you thought you knew. Conned. So let me bring you back to the question we started with. How big is the universe? Here's what we know. The observable universe is about 93 billion light years in diameter. We can see this far. No farther, and not because space stops here, but because light from farther away has not had time to reach us. Beyond the observable universe, there is almost certainly more universe. How much more we do not know. The geometry measurements tell us it is flat or very nearly so, but flat does not mean infinite. The topology could allow it to wrap back on itself on a scale we cannot currently measure. The large-scale anomalies in the cosmic microwave background hint that the universe might be finite, that there is a scale beyond which the fluctuations simply do not exist, a largest possible wavelength set by the size of the space. Eternal inflation suggests that our observable universe is a bubble in a vastly larger inflating space, with a boundary where our inflation ended and the surrounding inflation continues. A boundary that is not a wall, but a transition in the state of a quantum field. Quantum gravity approaches suggest that space itself is emergent, that at the deepest level, it is a collective, organized state of underlying quantum degrees of freedom, with the possibility of a phase boundary where that organized state ends and something prior to geometry begins. And the holographic principle suggests that whatever the universe is, it is in some sense equivalent to a lower dimensional quantum system without gravity. That the three-dimensional space we inhabit is a holographic projection of information encoded on some boundary. And that the edge of the universe might be the edge of that encoding. These are not contradictory pictures. They are facets of a single deeper truth that we have not yet fully grasped. Each one illuminates a different aspect of the same profound reality. And together they point toward a universe that is stranger and more finite and more structured and more surprising than the comfortable infinite expanse we defaulted to for. So the universe has an edge, not necessarily in the simple sense of a wall you could travel to, but in the deeper sense that space is not infinite, that it has a structure, a topology, a size, a boundary written into the geometry of reality at the deepest level, and beyond that boundary, in whatever sense beyond applies, lies the pre-geometric quantum reality from which space emerged, from which the Big Bang erupted. from which the 13.8 billion year story of matter and energy and stars and planets and life and consciousness unfolded. We are inside the universe looking out, bounded by horizons we cannot cross, surrounded by space that may be finite, embedded in a quantum reality that is deeper than space. And we are the part of that reality that became complex enough to ask about its own boundaries. The universe drew a line somewhere, and we are on the inside of it, looking at the data, building the mathematics, asking the questions, pushing the boundary of understanding, even as we cannot push the boundary of space. Bing. And here is what I want you to carry with you. The fact that the universe might be finite does not make it small. 93 billion light years of observable universe, possibly more beyond that, possibly much more, contains 2 trillion galaxies, each one with hundreds of billions of stars, each star potentially with planets. The scale of what is here inside the boundary is so vast that a finite universe is still more than enough to inspire a lifetime of awe. More than enough to humble every pretension to cosmic significance we might have. More than enough to fill every telescope we will ever build with more wonders than we will ever have time to catalog. The universe drew a line, and inside that line, it put everything, all the matter and energy and structure that 13.8 billion years of cosmic evolution has produced. All the stars and galaxies and black holes and nebulae and planets and oceans and mountains and organisms and civilizations and ideas and questions, including this one, including the question of where the line is. We are the universe asking where it ends. It's crimes. And the fact that we can ask, that we have the mathematics and the telescopes and the satellites and the theoretical frameworks and the intellectual courage to even approach the question. That is the most extraordinary thing about being alive in this particular moment in cosmic history. The universe has an edge. It's God, and we are just beginning to find it. Meditate on that.